Continuing our run through stats 2, let's have a look at the central limit theorem. Again, this worksheet's been taken from Miss Harris. All credit goes to her. If x1, x2, and so on up to xn is a random sample size n taken from any population, so before we had just a normal population, now this can be any population where the mean is mu and the variance is sigma squared, then for large n, so let's say any n bigger than 30, the distribution of the sample mean x bar is approximately normal, i.e. x bar is a normal distribution with the mean previously and variance, the previous variance divided by n. The approximation gets better as n gets larger. So that's why we're saying we need a large n to start off with. If a random sample of 30 is taken from a Poisson distribution with lambda 4.5, find the probability that the sample mean is greater than 5. So we can have a look at our sample mean. Let's call that x bar. We can say that x bar is normally distributed with mean. We know that the mean before was 4.5, so our new mean is also going to be 4.5. And we know that the variance of our Poisson distribution was 4.5. Now, because the sample size is 30, and we know that our variance is sigma squared over n, our new one is going to be 4.5 over 30. Now we've got to a normal distribution, and it's just a straightforward normal distribution question. As always with normal distribution questions, I would recommend sketching a normal distribution. We have z for our standardized normal distribution, x bar for our sample mean, and we're going to have 0 and 4.5. So the question says, find the probability that the sample mean is greater than 5. So here we've got our sample mean is greater than 5. The first thing we're going to have to do is find our z value to look up on our table. We're going to use our z value is equal to our 5 minus our 4.5 over root of 4.5 over 30. Which when I put it into my calculator gives me 1.29 to 3 significant figures. So let's put that onto our diagram, 1.29 to 3 significant figures, and I can look that up on my normal distribution table. So I'm going to grab my normal distribution table. As before, it's on page 19. I'm going to look up 1.29. So my table tells me that the probability that my z value is less than 1.29. Now I'm actually going to use 1.291 because the exact number on my calculator is 1.29099. So that's going to round to 1.291. And that's going to be 0.915 plus 2 on the last digit, so 0.9017. This number tells me this bit of area, it's the area less than my z value, but I was looking for this blue area to start off with, so for that I'm going to have to do the probability, which is what I actually wanted, that my x bar was greater than 5, is going to be 1 minus this, which gives me 0.0983. Let's finish off by having a look at an exam question. Here we've got the question from the June 12 Statistics 2 paper, question 2. For the continuous random variable v, it is known that the mean is 72. The mean of a random sample of 40 observations of v is denoted by v bar. Given that the probability of v bar is less than 71.2 is equal to 0.35, estimate the value of the variance. We know using central limit theory that v bar is approximately normal with the mean staying the same as it was before, so 72, and the variance becoming the original variance squared divided by n, and in this case n is 40. So the question is, how do we know that we need to use the central limit theorem? Well, the central limit theorem says that we can use it even if we don't know what the population is. So if we'd known that the population was normal, we wouldn't be using it, but we don't know what the original population is, but we do know that our sample size is quite big, so we can use the central limit theorem. Now we get on to the normal distribution part of the question. So we have our curve. Again, I'm going to put my z and my v bar for my normal distribution, and I know that my mean of z is going to be 0 and my mean of v bar is going to be 72. The information we're given is that V bar is less than 71.2, or 71.2 is this side of 72, and we're told that this area here is 0.35. Unfortunately, we can't find numbers on this side of our graph, so I'm going to have to look at the equivalent area on the other side. So this area is also going to be 0.35, but we can't look up 0.35 on our table either. So what we need to do is we need to have a look at the rest of the graph. So this bit which I'm shading in blue, all of the rest of the graph that wasn't that red bit of area. We know that the total area is going to add up to 1, so this must be 0.5. So now I'm going to try and find 0.65 on my table. I can't find it exactly, but I know it must be between 0.38 and 0.39. I need to add on about an extra 20. So my Z value is going to be something like 0.385. Possibly 0.386, you could go in the middle. I'm going to stick with 0.385. But this is on the wrong side for my normal distribution graph. I needed the value here. Well, because it's symmetrical, I know that this value must be minus 0.385. So now I can use my formulas. Z equals V bar minus the mean over the standard deviation. Well, here we've got the variance, so it's going to be the square root of my sigma squared over 40. And now I can start substituting in some numbers. So I know that my Z is minus 0.385, and that is equal to my 71.2 minus the mean, which is 72, over, and this is going to be sigma over root 40. And now I just need to solve that to find out what sigma is. So I'll bring my sigma over root 40 up to the other side. I'm going to divide both sides by my minus 0.385, and I get 2.0779. So we can work out what sigma is, and therefore we can work out that sigma squared is this times by root 40, and then we just need to square our answer. And we get 172.7. So 173 to 3 significant figures. For part II, explain why you need to use the central limit theorem in part I and why its use is justified. Well, we've got to use it because we don't know what the original distribution was, and it's justified because n is large. And that's the answer to the question.